All right, my friends, let's have some fun with macro markets and quant scenario analysis. You're making a forecast. You want to know what's the likelihood of a particular realization occurring. That's what I want to focus on today. We'll do that in the context of national income. All right, so let me see if I can zoom in a little bit here. If you're following along, the R code, if you're in my class, you're going to have the QMD file. If not, I'll have a lot of the code chunks here so you can follow without it. Case study KPI is going to be nominal GDP in your national income. Think about that like top line revenues. That's your P and your Q. Think about your probabilities as branches. Each branch is a different realization. And on each branch, you have what's the value of your forecast and the probability of your forecast in this video. We want to focus on those probabilities, okay? So we'll do a little bit about how do you make that forecast, but the focus is on the probability of each branch. So we'll go through the concepts statistically, economically, and in the code. So we'll clean it up and then we'll add on our packages. Several available. There we go. Next up, we want to use Fred to grab our data. We're going to use the FredR package. The way that I call it in is first I read in my key. I like to keep the key separate rather than telling the whole world on these videos what is my key, or the two people who watch the videos what's my key. And then the FredR set key package to call that in. That should open up a port to Fred. Now you and Fred are talking, your friends, and you can start grabbing stuff from him. And what you're going to grab is GDP, Series ID GDP. That's nominal GDP. Quarterly, we're not going to send an observation beginning date. That's going to be from the first date available, around 1947 or so, I think. And then we're going to end it on some random date. We're going to call it 2023. Now, what you could wind up doing is picking some local horizons that you want to examine the probability, The problem with that for forming probabilities is you need a nice range of options. You need a lot of data. So we're going to go everything from the beginning up until that end. Now, when you pull data from Fred, it's going to have a lot of extraneous information. I only want the date and the value, so I will use the select command. That will all be formed in my nominal GDP data frame. I'll clean it out with na.omit. Then I'm going to look at the growth rate. Mutate allows you to go ahead and, in a Dippler context, make something new. We're going to make something called delta. It's going to add the delta object to the nominal GDP data frame. It's going to use the lag operator. Now, what I could have done inside of the Fred call is actually pull in a period-to-period change. I wanted to show you could do this pretty easily as well with the delta. Now I'll plot that out just so you can see what it looks like. And I use a ggplot for that, nominal GDP, date and the Y on the delta, and some bells and whistles. And you could see what is the object we're trying to analyze. And then crazy is the COVID. Boom, it bust. All right. So now scenario probabilities. So let's say you forecasted nominal GDP in each of your scenarios, whatever was your framework, throwing a dart at the board, never do that, or some other subjective or quantitative model. It's natural to come up with a point forecast for each scenario, right? Maybe your worst case scenario, your bottom branch is saying nominal GDP is only going to be 0.5% growth. To quantify the probability of that happening, um, statistically speaking, we don't want to use it as such a fine razor's edge. If you remember, whenever you were looking at probability distribution functions in your stats class, what was the probability of a particular number, like 1.002? It was zero, or it approached zero. What you did was you actually looked in ranges. The empirical counterpart of that PDF was a histogram, which binned in ranges and then computed with the bars, the heights, the amount, the empirical frequency. Similar idea here. So what we want to do is, let's say you came up with a point forecast of 0.5. Let's put a range around that. I'll just, put 0.1 to 1, 0.001 to 0.01. So what's the probability of that occurring? What's the probability nominal GDP will be in that worst case range? I went this way. This way, right? The branches go down this way. So what you could do, and one method of many, 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 is look at the history of your target being in that range. You look back through time. Okay, I'm saying 0.01 to 1%. What's the likelihood? How many times have I seen it in that range? So what we can do is create the objects for that range. And again, subjective, you choose that. Doesn't have to be symmetric around your forecast, but it's nice if it is. And then what I want you to do is construct the density of nominal GDP, the histogram. And so I'll convert it to freq equals false, pardon me. Inside of the hist function within base R, that turns it into a density rather than an empirical frequency histogram, regardless. So remember it was 0.001 to around 0.01. So if you see my cursor, it's in like these few bars over here. So what you would do is you add up those bars, maybe 0.1, 10% plus part of this guy here. It's hard to tell. Is it 0.3? Is it 0.15, 0.2? You could try to ballpark it, eyeball it from that, but let's count it. And the way that you would count it is let's add together all the times that the nominal GDP delta, the delta that we made, is between lower and upper. So what this will do is it'll create a Boolean variable, a 1 or a 0, one hot encoded. It'll look down that column and say, if it's in that range, 1. If it's not in that range, 0. And then I'll add all those things up. There's 54 of them that are in that range. Well, that's a count. I want a probability. I want a relative frequency. So I'm going to divide by the total number of quarters that I have, which I think was like 300 something. And that gives me about 17%. So it's that 10% bar there and maybe, that 1% bar there and part of this bar over here, that's about 17%. So that would be the probability of that worst case scenario. Now, there's a lot of other ways that you can go about this. That's just one. Another way was suppose you used an empirical model to come up with a forecast, right? So you don't have a forecast for the best, for the middle, and for the worst case. You just have one forecast that's empirically based. And then what you want to do is say, well, what's the likelihood, probability that my forecast is wrong and actual GDP is going to be less than that, right? I'm going to say less because we're thinking about worst case. So we're going to build a forecast. And then we're going to say, well, based upon the uncertainty of the data, the uncertainty of my forecast, what's the likelihood that that point forecast actually, generates something that's lower than that? I'll show you a way to build a forecast called an ARMA, A-R-M-A, but that is one of many, 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 many different approaches. In fact, that's a whole course, whole field of study called time series analysis. So let me show you one. First thing we're going to do is set up our data for a time series model. We'll use the time series TS package. First thing that we're going to do is grab the first observation. Then we're going to create a temporary object. We're going to scrape off the date. Minus date means scrape that off. ngdp.ts, create a new object, time series, TS, time series object. That's going to take that temp. We're going to order it by the dates, and we're going to tell it the frequency, quarterly 4. We're going to start it at the first observation and then a monthly data. Now, frequency is 4 per year, but it's still going to indicate it on the dates. So it'd be, first quarter January, second quarter January, March, April, and so on and so forth. And then we'll set up the XDS, which is another time series object. In order to use these types of time series features, what you want to have is a rigorous forecasting approach. The rigor is going to come in part by making sure you're not cheating. I don't want to forecast on the data that I'm using to build my model. That's cheating, right? I don't want to use all the data I have, including the year 2023, to forecast the year 2023. I already knew it. My model already incorporates it. I'd be cheating. So what do? Create 2 samples out of the data that I have. We're going to use a test and a train. So what I'll do is I'll take the last 6 years of my sample and call that a test period. And I'm not going to test on the whole thing. I'm just doing that for illustration. Last, obvious. What's beautiful is that since it's time series, I could say, take the last 6 years, it looks like language, right? It looks like an LLM of this nominal GDP.xts object that I made and call that the test period. And now create a window of time of the nominal GDP object that starts from the beginning implicitly, I'm not including it, and ends right before my test period begins. So we're going to go my whole timeline. We're going to take the last 6 years, test that. Now, what I want is the quarter right before that. And that'll be the end of my training period where I'm actually building my model. So I have to go right before, 1 quarter before. See, that's minus 1/4, 1 year, 1 quarter. So you're going to take the last 6 years of nominal GDP, grab that number, kick back the quarter before it, and find for me the index of that. We'll clean it up, and that'll be our training period. Next up, we're going to train one of our, I'll call workhorse time series models, REMA. ARMA. Don't worry about the I, autoregressive moving average. I'm not going to train you on that right now. I'll have other videos on that. The basic idea is autoregressive, moving with its own past. If it's rising today, it'll probably rise tomorrow. If it's falling today, it will probably fall tomorrow. How far back into the past do I remember? The ones tell me how far back in the past I'm looking. This is just standard. We can be more optimal, but I'm going to train with this function called ARIMA on that training, only on the training data and the rate of change with this 1-1. Again, that's the workhorse model. We could be more specific about that later. Now I call that train.arima. That's on the beginning of my sample. Now I want to forecast into that period. So I will forecast. This beautiful XTS time series package speaks like natural language. Forecast that model 1 period ahead. H equals 1 period ahead. Grab that forecast, $ peek into it, mean. And that's saying that it'll be about 1.4% in that second quarter. What I want to do now is build uncertainty around that forecast to get to probabilities. Now that we have that forecast, what we're going to say is, well, what if I'm different than that? Well, what if the actual value is not 1.4%? What if it's down to 0.01 to 1% range? What's the likelihood that there's uncertainty around my forecast that would generate that? So what we'll do, and there's many approaches, we'll add some noise to our forecast. And then we'll say, based upon that noise, what's the likelihood that I would have seen something in that upper and lower bound? So we're going to start with just simple random noise that's calibrated to the volatility of nominal GDP that we've seen historically. So we're going to compute that volatility with the SD command, standard deviation. And then we're going to simulate. In R, what you have to do is use the R norm for normal distribution. Num sim, how many simulations you want. Set seed, any stats program you're going to use. When you want to simulate, best practice, choose a random simulator seed. That tells you where to start so that if you hand this code to somebody else, they're going to get the same numbers as you. Our norm, 5,000, set that equal to 0 for the mean. What we want to do is build around that forecast, right? So we're going to pick from that forecast and then say around that, based only on the variability from this Gaussian distribution that's calibrated to what nominal GDP usually shows. We're then going to add that noise, see right there, noise that we just made to the forecast. So we're going to take that 1.4 and add on a bunch of Gaussian noise. And we're going to say, based upon those new forecasts, right, that hit 1.4 plus some variation, what's the likelihood that we're seeing something in the range of 0.1 to 1%? So what's the likelihood we're seeing something in this range? Again, we could eyeball it from the histogram. What's going to be better is if, once more, we count between the worst case lower bound and worst case upper bound. And then we divide by the number of those observations, and what you get, 21%. So there's a 21% probability that we're going to get something as low as 0.1 to 1%. That's decent. It assumes normality, ignores the inherent structure of our forecasting model, but it's pretty good. So give me one sec. Okay, so what if we don't want to use just standard noise, right? Standard Gaussian noise. What if we want to be a little bit smarter? Method three, we're going to use the standard error from the model that we made to form the prediction interval. Um, so what would be an advantage of this? Well, we have a model, which means we have some structure. And all of these models and their structures are going to have some built-in variability, prediction intervals based upon standard errors. So let's grab that standard error. If you think about a 95% prediction interval, what you have is this range. I'll use the hat to represent my predicted value of my object at nominal GDP. Um, minus the standard error times the z-score. Oh, I got a little typo. There should be that little x there. Minus the standard error times the z-score, and the nominal GDP plus the standard error times the z-score. And that range, that interval, should be equal to 95%. So with 95% probability, I should be able to cover the truth. Now it's going to be centered around that forecast. So can I get to the object of interest that I want here? Like I said, I'm going to build it around the standard error. Well, when I estimated my model and I built that forecast, I have the upper and lower bounds already available through R. So can I just back out what I don't know, which would be the standard error? Well, I have an upper bound, I have a lower bound, and I have a z-score. If I have those three, I can get the standard error. So let's do that. Let's grab the upper and lower bound. Dip into the ARMA forecast, go to the lower, go to the upper. Number one just means whatever is that value. And then plug into that little formula that we just back of the envelope. Now, you're going to take the upper bound minus a lower bound, that's the numerator, twice because it's a two-sided interval. And then Q norm is going to be the function that's going to allow you to compute that z-stat effectively. Right? If you plug in whatever is that value, what's the probability associated with that? Then it's standard normal. Now, 0.975, I thought you said 95%. Well, if you remember your stats, right? Well, 95% coverage interval. We want it to be symmetric. So how do I cover 95% symmetrically? What you're going to do is start at the 0.975 all the way down to the 2.5, and that'll be a range of 95%. Right, cumulative. So with that, then, I'm going to take that standard error that we just derived back of the envelope. We're going to reset the seed. We're going to go back into my random normal generator, put together numsim. I said that was 5,000. Again, hit it at 0 so that I can add the noise on. But now I'm going to customize that noise for what's the built-in variability in my model, that standard error. Add that noise to my forecast, that ARMA noise, to my mean forecast of around like 1.6 or whatever it was, and then look at the distribution. So my forecast, that number, and then the range is around it. What I want to do is just like before. Well, you look at my cursor, it's from like 0.01% all the way up to around 1%. And I would add up the heights of these bars in relative terms. But you could be better about that. You can actually go ahead and count how many of those are greater than the lower and less than the upper bound. Very similar format to the before. And then divide by the total amount of them, the length of the sim values. And that gives you about 22%. There's another technique that we can have here. So suppose that the distribution around your forecast was Gaussian, calibrated to the standard error of your model. What probability would you see? We could use a more formulaic approach rather than a simulated approach. So I would use a formula based upon a normal distribution. And that's going to be the P norm. Now, the P norm is basically saying, like you've done before, you take your CDF, remember the cumulative density function? And whenever you did that, what you're doing is taking from that point all the way back to the origin, back to that lower bound. So it's a probability it's less than or equal to some point. In this case, the probability it's less than or equal to the upper bound, where the mean of that normal distribution is centered at your forecast, and the standard deviation is based upon your standard errors. But that's only going to give you the region below that upper bound. What we want is between the upper and lower bound. So we're going to reconstruct that for from the lower bound over. Worst case dot lower. Same mean, same standard error. Now, how do I get in between those regions or between those points to get to the region probability? Just subtract. Probability 1 minus probability 2, and that is about 23.5%. So that's the probability you might fall in there. We have multiple methods for this. Here's another one. Suppose I don't want to use any of this assumption of Gaussianity. Rather than using the CDF that we just did with p-norm, let me use the empirical CDF, which is basically saying, let the data speak for itself. Let me look at the residuals, the errors, where my model went wrong. How are they shaped? They could be Gaussian, they could be student T, they could be anything. And let me grab those, look at the density of those, and use that as the noise. There's lots of ways you can extend that with bootstrapping, etc. So let's grab the residuals with the residuals command on the model that I trained. I'm going to resample from that. Now, how do I resample? Theoretically, what you're doing is, remember in stats class, you had this urn with colored balls and you took out, oh, it's blue, oh, it's blue, it's red, it's red, it's orange, it's blue. You had a couple of choices for that to get to the empirical probabilities. You could resample with replacement or without. Here, we're going to do it with replacement. NumSim times, I think it was 5,000 on those residuals. So we're going to resample from those residuals lots of times. Resample.residuals. Then what I want to do is take my mean forecast at 1.6 and add on a whole bunch of this noise from the resampled residuals to see how far it typically goes to the left or to the right of my forecast. And then I want to count how many of those are, once again, this will look familiar in the code, greater than the lower bound and less than the upper bound. Count them up. Calculate the probability by dividing by the number of those. That's about 21%. So we have lots of different approaches to this. Let me summarize. So I want to get the 5 probabilities, create this new data frame called method, and then group them together in this vector of the different probabilities, order them. Okay, so take the prob values, and it's going to be this data frame. I want to order the data frame in descending value on the probability column. So this is prob values, order on the probability column, hence the $sign. The negative sign tells you descending rather than ascending order, and then print them out. Those are the 5 probabilities. So the highest probability of being in that low branch, that 0.1% to 1%, is 23%, down to 17%. They're all relatively close. So here's the summary theoretically. What's the empirical probability of nominal GDP being bad? It's labeled worst case, but bad, meaning it's only 0.1% growth to 1% growth. The first method was, well, historically, how often did it fall in that range? The second case is, how likely is this range if the deviations from my forecast, that fancy ARMA model, you could have done other stuff, are random Gaussian noise calibrated to the historical vol of nominal GDP. The method 2 is, how likely in this range if the deviations, how likely is this range, pardon me, if the deviations reflect the model's own forecast uncertainty. 4, what if I use an analytical formula that's built around a Gaussian model? Now that formula from model method 4 is, it sounds a lot like method 2, but method 2 is simulation using the empirical sigma. 4 is a formulaic approach, assuming Gaussianity. And 5, how likely in this range is this range to occur for my nominal GDP if I relied on the data, the empirical density, rather than normality. All various approaches, certainly not exhaustive, but I hope helpful. Good luck.